Buffer solutions resist changes of pH upon the addition of small amounts of either acid or base. So when I put hydrochloric acid in water, the pH goes way down. If I put hydroxide in water, the pH goes way up. If it's a buffered solution, there's something in the water that'll eat up that H plus ion if I add the hydrochloric acid. I got a weak base in there that'll eat it up. If I add hydroxide, there's something in the water floating around in there that'll eat up the hydroxide. So the pH doesn't change that much. So different buffers buffer at different pHs depending on what the Ka of the weak acid or the Kb of the weak base is in the buffer. So for example, if I have a hydrofluoric acid fluoride ion buffer, right, equal amounts of hydrofluoric acid and fluoride ion, if I add hydroxide is going to be eaten up by the hydrofluoric acid, and the pH isn't going to go up so much because that hydroxide's been removed. It's reacted with the hydrofluoric acid, so the fluoride ion concentration goes up. Right, that's what you get when you take the H off of hydrofluoric acid, and the hydrofluoric acid concentration goes down, but it doesn't spike up because you're not putting all that hydroxide in there and having it sit. It gets eaten up. Same with H plus ion. The pH doesn't go radically down if I add hydrochloric acid to the solution because the H plus ion is going to react with the fluoride ion to increase the hydrofluoric acid concentration and produce fluoride ion. But the H plus ion from, let's say, like the hydrochloric acid that I add gets eaten up. Sodium acetate and acetic acid buffers. All right, so again, right, let's just start off. I got equal amounts of acetic acid, a weak acid, and its conjugate base. Like if I put a bunch of sodium acetate in there, I've got the acetate ion in there, its conjugate base. So if I add H plus ion to this, the acetate ion will eat it up and make more of the acetic acid as the acetate concentration gets lowered. So let's say I'm going to add hydrochloric acid to my buffer. See, I've got acetate floating around in the water. I've got acetic acid floating around in the water. I add, 3 moles of H plus ion to the water. Well, the acetate in the water eats up that 3 mole of H plus that I added, and the pH doesn't go way down now because that H plus is gone. It's been eaten up by the acetate. So now all I've had left here is acetic acid, a little bit of acetate, right? So pH may go up a little bit, but I still have a common ion situation where I've got acetate in here suppressing the weak acid. So the pH isn't going to go down all that much. I guess that's what I meant. Go down all that much, right? Goes down when you add acid. So we're protected against a spike in H plus ion being added because it gets eaten up by the acetate. There comes a point that we've overwhelmed the buffer, right? So let's look at that again, right? So at this point, I've got 1 acetate left in there. If I add 2 drops more of hydrochloric acid, the buffer's overwhelmed, right? The acetate's burned up, and now that last drop of H plus, the pH goes way down because I've added a bunch of H plus to the water. H plus is floating around there, and there's nothing there to eat it up. So the pH goes way down because I've got H plus floating around. H plus added is now greater than the acetate concentration in the buffer. pH is lowered dramatically now. You've eaten up the buffer. If I'm protected a bit against H plus being added to the solution, like with this buffer, I'm also protected against hydroxide being added. If I add hydroxide to this buffer, the acetic acid in the solution is going to eat up the hydroxide. So the pH isn't going to go up so much, right? If I dribble in, 3 moles of hydroxide, it eats up 3 moles of the acetic acid. I still have a common ion situation between the acetate ion and the acetic acid. And the pH doesn't go up very much, right? There's no hydroxide left. It got eaten up by the acetic acid. But I can overwhelm this buffer too, right? If I add enough hydroxide, I eat up all the acetic acid. Now that last drop of hydroxide has nothing left to eat it up, and the pH goes up, like we'd expect if I put hydroxide in water. All right, so calculating the pH when you've got a buffer is just a common ion situation, right? So we could solve for the Ka and find out what we could solve using the Ka and find out what the H plus concentration is and then take the negative log at the pH. Or I could plug into the Hasselbalch equation. Either way I get the same answer. So solving a Ka problem for this where I've got acetate suppressing the weak acid, or the other way, right? Plugging into the Hasselbalch equation, I get the pH either way. All right, so which of the following systems are buffers? So if I have equal amounts of potassium fluoride and hydrofluoric acid, this is the definition of a buffer. I need a weak acid and its conjugate base, because only its conjugate base has any kind of significant strength because it's a weak acid. Whereas with hydrobromic acid, bromide ion has no basic properties. It's not a base. So if I put hydroxide in a potassium bromide hydrobromic acid solution, there's nothing there to I'm sorry, if I put H plus in here, there's nothing there to eat it up. The bromide ion is a non-base. Sodium carbonate and sodium bicarbonate. Yeah, this is a weak acid and its conjugate base, right? Take an H off of bicarbonate and you get carbonate. So yes, you've got a weak acid and its conjugate base. So this constitutes a buffer. Calculate the pH of a solution where you've got 1 molar acetic acid and 1 molar sodium acetate. So if I want to solve for the pH, it's just solving for a common ion, right? Take these concentrations, right, recognizing that the amount of acetic acid is going to be suppressed. The amount of acetic acid disappearing is going to be suppressed because of all the acetate you've got in there. So the acetate concentration isn't going to go up at all, and the acetic acid concentration is not going to go down at all. So I can just plug in, right, and ignore the change in each of these. So 1 divided by 1 is 1. So the H plus concentration is equal to the Ka. Take the negative log of the Ka and you've got the pH. What happens when you've got a 0.1 molar gaseous hydrochloric acid added to 1 liter of this solution? Well, if I put a bunch of hydrogen chloride into this, the hydrochloric acid is going to be eaten up by the acetate that's in there. So I'm going to lower the acetate concentration, right? This is a neutralization reaction. This goes all the way forward, right? This has a very large K value. So you can basically look at this as a limiting reactant problem. You put H plus with acetate. The acetate eats up all that H plus. You lower the acetate concentration, raise the acetic acid concentration. So now you have new concentrations. It's still a common ion situation. So just take moles of the acetate left over, moles of the acetic acid, plug into the Ka expression, and solve for the H plus concentration. Again, these concentrations aren't changing very much because of the suppression of the ionization of acetic acid. So I could just ignore how much acetic acid I'm losing, acetate I'm losing, and just plug in and solve. I could also just plug into the Hasselbalch equation, right? So plug into the Hasselbalch equation, plug in moles of acetate and moles of acetic acid. Since it's moles per liter divided by moles per liter, whatever the volume is going to cancel. So I can just plug moles into the Hasselbalch equation and get the answer. So plug in the Ka and solve, and you've got the pH. What happens when 0.1 molar of solid sodium hydroxide is added to this solution? Well, we're going the other way, right? The acetic acid will eat up the hydroxide, so I'll lower the acetic acid concentration, raise the acetate concentration, and if I want to solve for the pH, again, it's just a common ion situation. Plug those mole values or those mole per liter values into the Ka expression and solve for H plus. Again, I can ignore the change in the concentrations. Or I can plug into the Hasselbalch and solve for it. All right, when doing buffer problems, they always follow the same pattern. You've got a buffer, right? You've got a weak acid and its conjugate base in high concentrations, and then something happens, right? You add something to the buffer like hydrochloric acid, and those molar values of the weak acid and the conjugate base change. So something happens, like you add the hydrochloric acid, which is you treat as a limiting reactant problem, right? The hydrochloric acid is all eaten up by the buffer. And then you look at what you're left with. So it's some sort of Ka or Kb problem once the change has happened to the buffer. All right, so looking at an example, calculate the pH of a 0.3 molar ammonia, 0.36 molar ammonium chloride buffer system. So we've got a high concentration of weak base and a high concentration of its conjugate acid. All right, so calculate the pH of this system. All right, so this is just a common ion problem, right? We know what the concentration of the ammonia is. We know what the concentration of the ammonium ion is. So we just plug it in and solve for the H plus concentration, right? These concentrations aren't going to change appreciably as ammonium ion shifts towards making more ammonia. So you can ignore the change in these concentrations. So multiply both sides by 0.36, divide both sides by 0.3. We get the H plus concentration equal to the Ka. Or actually, it's not equal to Ka. I'm sorry, they weren't in equal amounts. So we get the H plus concentration. Take the negative log and get the pH. So hey, this is a buffered system up in the basic range. Okay. Same calculation, right? You could use the Henderson-Hasselbalch, right? So you could plug right into this equation. You get it on the test. It's just plugging in directly to find the pH, and sometimes this is just easier. Either way. All right, so now something's going to happen, right? We're going to add, calculate the pH after adding 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer. So the first thing to do is convert everything to moles. This is going to be a limiting reactant problem. We want to know how much hydroxide we have and whether that's the limiting reactant or not. So liters times moles per liter gives me moles of ammonia. Gives me moles of ammonium ion, and gives me moles of hydroxide. All right, so this is what I'm starting out with this limiting reactant problem. So convert everything to moles, and now we go back to the neutralization reaction, right? The hydroxide is going to react with the ammonium ion in that solution. So ready, set, go. All the hydroxide gets eaten up. You eat up some of that 0.0288 moles of ammonium ion, and you turn it into ammonia, right? So add 0.01 moles to your 0.024 moles of ammonia, and you've changed the mole values. Now at this point, guys, I'd encourage you just to take these mole values and plug into the Hasselbalch equation, right? We've got a common ion situation here. You don't even have to convert back to liters, right? Because those liters will cancel. So you take the mole values, all right? Again, I plugged in the liters here, but you really don't have to, right? You don't have to turn it back to concentration units. The liter of solution will cancel. So 20 milliliters and 80 milliliters is 0.1 liters, 100 milliliters. So divide that into moles to get the concentration, if you will, and then plug it into the Hasselbalch equation and solve for the pH. It would have come out the same if you just plugged in moles. So hey, the pH, we added hydroxide, the pH went up, but not that much, right? You only ate up a little bit of the ammonium ion, right? The ammonium ion was still there, and so the pH went up, but it resisted a change in pH because you had that ammonium ion in there to eat up that hydroxide added.